Значит, что мы приготавливаем начальное состояние, затем вычисление, это манипуляции, так сказать, вот этими квантовыми вентилями, либо однокубитными, либо двухкубитными. И всегда это чаще всего бывает комбинация того и другого. И после этого измерение. Вот. Ну и как бы независимо от того, sorry, switch to English, irrespectively of the type of the hardware which we use, this could be atoms, ions, or superconducting qubits, there are certain requirements. And those requirements actually were not obvious in the very beginning when people were suggesting to do it in theory. But then around the end of the last century, people have really needed to compare different platforms. And the accepted approach to compare different platforms, if they're good or bad or beneficial for quantum computing, is based on the so-called DiVincenzo criteria. DiVincenzo is a physicist, mathematician and physicist who worked in IBM for many years and who is now working in Germany in the University of Aachen and Research Center in Jülich. And David DiVincenzo formulated about 25 years ago the criteria which are required for a functionable quantum computer. At that time, there were no quantum computer yet, but these criteria were very relevant to on the path to realize it. And first criterion, of course, is that we have a well-defined, extensible or expandable qubit array. So array of qubits on which we could do one qubit gates and 2 qubit gates. Now, very important is that we need to prepare a certain state. And the most simplest state, of course, is the lowest energy state, which will be in conventional notation 000 state of all the qubits. The second criterion is to have a really long coherence time, because if we manipulate too slowly, if our gate is too slow, then the result will be meaningless because we have lost all the information on the way. So the gates must be much shorter than the coherence time. Besides that, we also need to have, of course, this universal set of operations, which means at least one 2-qubit gate and several single qubit gates. And also, very important is really to be able to measure the state of the computation, to be able to measure, if possible, simultaneously, the states of qubits in the array. So these are the five criteria which are relevant to compare different approaches. And some technologies satisfy them, some of them not satisfy them sufficiently. On the list of DiVincenzo criteria, there are two more. You see him actually my picture from back 10 years ago when he was coming on my invitation to colloquium in Karlsruhe. He has two more, which is interconvert stationary and flying qubits, which means that we need not only store the information, but also transfer the quantum information over distance. And the seventh is transmit flying qubits from place to place. Well, transmitting and interconverting flying qubits is a technique which is used in quantum communication. But sooner or later, quantum computing will develop, and obviously quantum networks will be required, which means that one will need to couple quantum computers into a network. And if you couple classical computers into a network, then by adding two identical computers, you double the power of individual computer. If you connect quantum computers into network, you expand your Hilbert space. You basically increase the dimension of Hilbert space by many times equal to the number of qubits in the additional computer. And basically, you multiply the power of computer. Therefore, until now, people were not really focusing that much on the 6 and 7 points of DiVincenzo criterion, but they're very important for the future. When quantum internet comes, then by implementing that, one should be able to multiply the power of quantum computers coupled into such a quantum network. That's very, very interesting. Okay, so let's talk about the coherence very briefly. There are two types of processes which are important for the coherence. First is that the qubit can change its state in a way that you go from high energy state to the low energy state. You go from state 1 into the state 0. And this process is called energy relaxation. In this case, you exchange energy with the environment, and you basically lose, with this energy, you lose the information. Another important type of decoherence is the dephasing. And this is basically losing the phase memory of the qubit. So once you have the state of the system into the Bloch sphere, and then you prepare some state on the equatorial plane, then, for example, variation between the energy level separation between the levels will make the vector on the Bloch sphere randomly diffuse along the equatorial plane. And this will be a process called dephasing. So this phase memory and the dephasing is limiting the manipulation. So the qubits must stay coherent. But besides the manipulation, we also need to do the measurements, and energy relaxation is the key thing for the measurement, because we must be sure that the states are not mixed when we want to measure the result, which means measure the projection, for example, on the z-axis. So both these times T1 and T2 are very important, and extending them is a battle which every platform for quantum computer has to follow. Now the hardware. So in this lecture course, we talk about the hardware for quantum computing, and as I promised you, I will talk later on today about trapped ions. Maybe also mention today or in the beginning of next lecture neutral atoms. Then we briefly talk about the photons. I will not talk about spins in molecules, because this is not really scalable technology. Spins in molecules basically means that you can make a liquid of identical molecules, some diluted solution of molecules, and then study the properties of different spins, but you measure always the response of the ensemble of spins of many identical molecules. And the scalability here is limited by, let's say, maybe few or maybe few tens of spins. You cannot really scale more. But the first quantum computers, actually, the first quantum computer which was made in IBM, on which Chuang made his factorization of number 15 into primes of 5 and 3 back in the year 2001. It was made actually using photoform, if I recall correctly, solution. So this was used for demonstrations, but not really for practical development. Now, all these systems are microscopic, and they naturally exist in nature. So one has to learn how to manipulate them. One has to find the ways to isolate them and manipulate them and read their states in a very controlled way. However, there are also synthetic quantum systems, or if you want, engineered quantum systems. And these are systems we can prepare in particular in solid or in condensed matter. And these are, for example, defect spins in crystals, like defects in a diamond, for example. These are spins in quantum dots. Here you see there is a surface of a semiconductor. There is a two-dimensional gas below, and these are the electrodes which are used to deplete the two-dimensional gas region under the electrode, and then form particular configuration of two-dimensional electron gas under the structure. There are also other systems more exotic, like electrons on superfluid helium. There are also magnons. There are also polarons suggested, and so forth, or excitons. All these systems, they have to pass the De Vincenzo criteria test before being really seriously considered. And some of them really don't did manage to do it until now, but still physicists think of different alternative ideas realizing. The most promising and productive approach nowadays, that's where many industrial companies rush to work using engineered qubits, are the superconducting qubits, which we focus in the major part of our course of this lecture. Okay, so I'm a bit slower today, so this is a summary of the first lecture. We talked about the introduction. I remind you spin 1/2 system, remind you the Bloch sphere model to visualize the qubit states. We talked briefly about quantum gates and rotations on the Bloch sphere. We briefly discussed the decoherence, but we'll talk much more, of course, in application to different implementations of qubits in solid states. And really important is always to remember about those criteria, the Vincenzo criteria, which make it possible to realize a practical quantum computer. All right, let me stop sharing for a moment. I need to start the next series of slides. Any questions on the way? Comments, complaints?
All good.
Thank you. Any feedback is appreciated. All right. Okay, so this is the second set of slides where we're going to start talking about real physical systems on which quantum computers can be implemented. May I ask, have you heard any lecture on ions or atoms, qubits, some introduction or something? I'm not sure what was the first part of this course. You heard the quantum communication, or was it just theory in Fistech? The first half of the semester.
Actually, we have a year ago a course dedicated to studying different physical platforms. So we discussed it briefly, and we also have discussed what you previously mentioned, like De Vincenzo criteria. And
okay. Was it from Alex Fedorov or?
Yeah, it was from Alex Fedorov's group.
Good. So he's a great guy. He's a theorist. I have privilege or maybe a handicap of being experimentalist. Therefore, I think you have a different version from me. But some of things I think it's not bad to repeat after 1 year. Okay. So this is a slide you have just seen. And in this lecture, I have planned to tell you about trapped ions and neutral atoms. So we are going to briefly remember about electronic states of atom as a building block for nature. Atoms are very important and something you learned in a general physics course. I need to refresh here. And then we'll discuss about using ions as qubits, and then also continue with atoms, neutral atoms, not charged atoms as qubits. On the picture on the right, you see something which is often advertised, but I think it's not really a real thing. So these dots are ions, which are suspended in vacuum, somewhere here in this very little slit. And these ions are shining because of fluorescence, so they shine by illuminated by laser, and if they are in particular state, then they can make a transition to the fluorescent state, and then one can actually observe them with almost naked eyes. They're very small, but the wavelength of emission is of the order of micron, and having a light source of very small size makes it possible to see them under microscope. So there are two approaches, as you have seen. One can take an atom and either remove one or more electrons from an atom and get an ion. If you strip the electron away, then you have charged particles, and they will interact via electric field, via Coulomb interaction, just as charges. So they will be easy to control by using electric fields. Neutral atoms are a bit more tricky because they have no charge, but they are polarizable. So in the very same Coulomb interaction will make it possible to make atoms interact. But now you will have interaction between electric dipoles. And there are states of atoms in which one can form so-called Rydberg states. These are the states of an atom which is excited in a very high state of the primary quantum number n. In this case, the atom is almost ionized and then gets really large in size of the scale of a few microns, up to a few microns. And then the dipole moment of that can be quite large, and it makes it possible to observe interaction between neutral atoms if they are trapped in small distance between them. So these approaches require high vacuum technique. So basically one needs to bring those few atoms in very high vacuum conditions in some chamber, which has very low residual pressure. And then one needs also to have these additional instruments, those fields, electromagnetic fields, which can hold ions at particular place and also hold atoms. Now let's remind very briefly the basics of an atom. So if you have electronic state of an atom, of course in the center we have the nuclei, which is having a certain number of protons, which means has a certain positive charge. And then the electron around states existing around near the nuclei forms a bound state, and its state can be described in this spheric symmetric potential, where you could basically represent the electronic wave function as a product of three parts. One is the radial part, which is characterized by the principal quantum number n. Then there is an orbital quantum number, quantum wave function p, and the magnetic quantum number ml. And this approach of describing the quantum state of an atom leads to three Schrödinger equations, which can then in terms give the eigenstates with three quantum numbers associated with the energy levels. So the state of atom can be then changed between 1 to 3. This is the primary quantum number. Then these SPD orbital states are different numbers of the orbital quantum number L, which can change between 0 and n minus 1. And then, as you know, the magnetic quantum number will change from minus L to plus L, and this is associated with the symmetry of the wave function of electron and atom. So basically, this is the standard assumptions of the atomic physics, and the example of the states which are actually characterized by particular energy levels, and transitions between them can be measured by using optical spectroscopy. So one can either absorb the photons by making transitions between the different energy levels, or emit photons. Now, to make these transitions, atoms have to be, of course, should have some allowed transitions, and one has to take into account selection rules, meaning that a photon is a particle with angular momentum 1, so it's integer, and therefore the orbital quantum number can change 0, plus 1, or minus 1. Sorry, J number, excuse me. The orbital quantum number can be either change to plus 1 or minus 1 due to this angular momentum of a photon. Then the spin number doesn't change because the photon doesn't carry spin. And this J is the total angular number in atomic physics, as you know, is sum of L and S. And S quantum number is the spin quantum number. It can be either -1/2 or +1/2. So some of these transitions are allowed, some of them are not allowed. If transition is not allowed, that means that actually if the state has no opportunity to decay, for example, the emission of the photon in the free space is prevented by modifying the environment, the emission of the environment. For example, we have some resonator which has a different frequency, and then your so-called Purcell protect from the emission of the atom, a particular frequency which is different from the frequency of the resonator. So in this case, the states will live long time. And of course, some transitions are forbidden, but they are forbidden in the first order. So there will be, of course, some factors which will lead to those transitions, but they will occur at much lower rate. And that means actually you could have enough time to do the quantum computation if you use those states as your quantum states to encode your state 0 and 1. Since atom is strongly anharmonic system, it's very often the case that you could choose very safely a pair of transitions, and then the frequency of transition between those two levels will be unique, which means that actually if you apply photons of this frequency, you will not excite any other transitions. In that respect, you could use any convenient pair of states as for encoding the information in fashion of two-level system. Of course, you need also to make sure that you are able to read out those states, and you might need to make sure that you can manipulate those states. And this is a matter of convenience, and actually for a long time the job of physicists was really to find convenient transitions in particular elements. There are many elements, and transitions have different features and different characters. Some of them are very long-living, some of them are very short-living. So basically, long-living transitions, stable states with long-living transitions form good qubit states. But you need other states to be able to read out those states. That's, of course, also part of the requirements according to the Vincenzo criteria. Now, one can manipulate atoms with light, and as you know, in the hydrogen, there are different lines, a series of lines. The Lyman series starts from deep UV, deep ultraviolet transitions. Then Balmer series already enters the optical range of visible transitions. This is transitions between states N2 and equal 2 and N equal 3. And there are also other series, of course, most of them lie in the infrared range. So all those are optical frequencies with photons of the wavelengths of the order of a micron or less. And one can manipulate atoms with lasers. That's very convenient. On the other hand, there is also convenience of manipulating atoms by microwave frequencies. And this is in particular convenient because one can change the resonance frequency using microwaves. The resonance frequency is typically achieved either due to the spin interactions in an atom, for example, fine structure interaction or hyperfine structure interaction due to the interaction of electron spin with a nuclei, but also by applying magnetic field. And if you take, for example, degenerate state 2p, which have electrons with spin, with different spins, then you will have basically Zeeman splitting of this degenerate energy levels with states occupied by different spin states. And the transition lies in the range of some hundreds of megahertz or gigahertz, depending on the strength of magnetic field which you apply. So this can be either the fine structure type coupling due to the orbital coupling of the electron orbital motion up to the spin state, or the spin moment, or the externally applied magnetic field, as we all know. Now, how to use those transitions, we'll talk a bit later. Let's first talk about the choice of an atom. And one very particular atom, which is extremely convenient and very good for quantum technologies, is cesium atom. The reason is this is an atom which is standing in the periodic table next after xenon. Xenon has 54 nucleons. It's very stable. Nuclei also has all filled shells of electrons. And then by adding one extra electron there, one has the level structure which is extremely simple and stable in time, and actually is not depending much on the external factors. And this cesium atom has been realized to be very convenient to make, for example, metrology standards. What happens there is that you basically add to xenon atom this 6s electron, and then due to the hyperfine splitting of this level, the nuclei of xenon has the spin 7 or 7/2 measured in Bohr magneton, and the electron spin basically interacts with the spin of nuclei, and this splitting leads to the frequency of about 9.2 gigahertz. And this frequency does not depend on anything in the world. It's just characteristic for this particular type of atom. And therefore, cesium atom has been used for metrology, and it's now being used for defining the standard of time. It defines a second. Until 1967, the time was defined as a fraction with some crazy number in denominator. You see this crazy number, 31 million and some fractions of the tropic year for the year 1900, and particular day and so forth, because of course all these astronomical times are not really stable and only known from measurements. And after 1967, the standard of time is just a duration with this fraction of with this number of periods of radiation corresponding to transition between the two hyperfine levels of the ground state of the cesium 133 atom. So this is the standard, and actually the standards of time will be used for GPS for all the modern metrology. This work on this direction are also work in Russia in FIAN, for example, in laboratory of Nikolai Kalachevsky. They've been working on these metrology problems with these and other types of atoms for a long time. So there are also other types of atoms which have certain advantages and disadvantages for these metrological purposes. So this is a very convenient type of atom, and this can be used actually to. Do I have this here? Okay. This being used as a standard for quantum measurements already for a long time, but not for computing. Now, for computing, let us have this interesting slide. Have a look at this slide. I borrowed it from Gary Dell from a company called Quantum, which is a company dealing with atomic qubits. And this picture sort of summarizes here technological approaches to quantum computing. And here you see that one corner is filled with superconducting circuits. We'll talk about them in length later in this course. Now, these are trapped ion qubits, which we are going to discuss here. And these little abbreviations here are the companies, startups, or bigger companies like Google or IBM for superconducting circuits, which already started their programs and started developing commercial devices. So for ions, these are Austrian Quantum Technologies, founded by Rainer Blatt. These are IonQ, founded by Chris Monroe. And then Honeywell is the company which actually partially is a spin of IonQ, is already working already for a long time on this field. So it's really a platform which is having commercial approaches to use trapped ions for quantum computing. Here, for cold atoms, this era a bit younger. So there is a Q-era company founded by Michel Lukin and friends at Boston, around MIT and Harvard. Pascual is a French company, which is founded by their competitors, but there are also other companies starting around the world. So these are called atoms qubits, which are not using charged atoms, but other neutral atoms. Then there are also photonic qubits, which we'll talk about briefly, and also some more exotic qubits, which actually relevance was debated for a long time, and I think Microsoft has now closed this program, at least to the knowledge I have. They're not continuing in that direction anymore. All right, so how can we use an ion as a quantum bit? Very simple idea. So first we need to learn how to trap an ion in a vacuum. So we need to find combination of electromagnetic fields to hold an atom, an ion, somewhere in free space. Second is to select, we need to select some long-living states and encode logical qubits, states 0 and 1, into those states. It has to have unique frequency separation. It has to have convenient frequency range for manipulation. Typically, this could be microwave or can be also laser. Then to manipulate, typically we also need a laser or microwaves to excite transitions. Then we also need to read out, and typically readout is done not by microwave but by optics, because one can observe the fluorescence of emission of light from atom when atom quickly goes from some high excited state to the ground state. But the readout works that one can basically apply a laser pulse from one of the qubit states into this short-living state, which has this optical transition with high emission light intensity. So basically, if we have two qubit states here below, 0 and 1, we manipulate them by either by microwave or by laser pulses. We need also to read out, and we read out for the state 1, if the measurement finds the qubit in the state 0, then basically with 100% probability, we'll go to this short-living readout state, and then a fluorescence from that state to this state, or maybe to some other state, will lead to emission of photons. So basically, once you have the pumping pulse on, the fluorescence can be observed by a photodetector and a photon counter, and basically this will be the result of the measurement. The qubit was in the state 0. And then the probability of finding detecting different number of photons, of course, also depends on the resolution and noise in the detector. So this is an example of detector which has detecting efficiency of about 98%. So you detect some photons being emitted, and this will correspond to the state 1. But if there is no photons or only very few photons being emitted because of the noise and errors, this can be addressed to the state 0. Then by putting the discrimination line somewhere here between these black and gray bars, one can make an efficient detection efficiency. All right. So then next question is how to trap an ion. Well, namely, we just need some plates with electric fields. And if we take, for example, two capacitor plates with positive charge and put an ion in the middle, then ion will be sort of squeezed between the plates and cannot move up or down, but can always move to the side. Now, okay, so if we now fix the potential from the side, also put the plates, one can naively think that one can sort of localize ion in the middle. It doesn't work. And if you remember well your Sivuhin 3 part of the basic physics course, electricity and magnetism, there is the so-called Earnshaw theorem that a static combination of electric, magnetic, and gravitational field, which means the conservative fields, is not capable of keeping an object in a stable equilibrium. So we cannot find a stable equilibrium under the action of just these well-known fields. And there is not much more one can use. Gravitational field is rather irrelevant. Okay, it's maybe relevant for metrology when you make an optical clock out of cesium atom. That's where they threw the atom up and down in the clock and then cancel for the gravitational line shift. But magnetic field and electric field, which is available to manipulate ions, will not make it possible to keep the ion in particular position. Well, so this is a kind of problem which is not completely unexpected, but which is not simple to handle. And it was this gentleman. Okay, so maybe I'll tell you first. I'll tell you first something else. So if you want to suspend some ion in free space, you need to make a levitation of an ion. There are different techniques of levitation. This is a bit kind of interlusion, which I have here as a slide. Okay, you certainly know famous Nobel laureate from PhysTech, Andrei Geim, my friend, who did, before he got his Nobel Prize, he actually did an experiment for which he got an Ig Nobel Prize together with Michael Berry, the very same Berry who invented Berry phases, mathematical Berry phases. So they had a paper together, which was titled "Of Flying Frogs and Levitrons." And this very paper got a Nobel Prize, and I think it was 2000. Yes, it was 2000. Now, if you want to levitate something, then of course there are different techniques available, but none of them can be applied to ions. But just to mention, these techniques could be, for example, levitating a diamagnetic object in free space, and this is levitating a frog, which was done by Geim back in Nijmegen a long time ago. And the idea here is that if you have a diamagnetic substance, and any material, any organic material is slightly diamagnetic, so magnetic dipoles, intrinsic magnetic dipoles of the material, they orient themselves against the magnetic field, and therefore this material is being expelled from the region of high magnetic field. And it means that actually the diamagnets, they move along the field gradient. And the experiment they have done, they were putting a frog in the gradient of field of a high field magnet. So the high field magnet means that there is high field in the core of a magnet, in the tube, where the field is concentrated by solenoid and is parallel to the axis of the solenoid. But once the solenoid stops, there is a large gradient, so the field actually expands in free space. And that's where you have a gradient facing upwards. And in the magnet, a diamagnetic object may have position of equilibrium. This is really famous Friday experiment of Andrei, where they managed to levitate a frog in the opening of a magnet. Of course, you need very large magnetic fields, roughly 30 Tesla or more, which is difficult to get and is only available in few places around the world. But this really led to something noticeable by physicists on the sense of, particularly on the sense of humor. It was quite amusing. On the other hand, these things also exist, and this was also the title of the paper, the joint paper, Levitron. That's a spinning magnet which rotates in non-uniform magnetic field. So actually, it doesn't violate Earnshaw theorem because the fields here are not stationary. The fields are non-stationary due to the rotation of the magnet. And that's something which actually can be bought also in the shop. So these Levitron toys are available. One can make a levitation, not mentioning superconductors, of course. That's why you know the levitation experiment is first thing you do to show the diamagnetism of superconductor. So it's available also. And this Levitron thing is actually similar to the ways one can levitate an ion. And this was proposed by this gentleman. His name is Paul. He got his Nobel Prize in 1989, just for the fact that he was able to trap ions in free space and then do interesting experiments with them. And the idea here was the following. So he designed the so-called Paul trap. It's named after him, but there are also other traps which can be realized. And the idea is not to use the stationary potential, to use non-stationary potentials. For example, if you imagine there are two rods like this, on one diagonal, and then two rods on the other diagonal. And then you connect here some radio frequency source, for example, a frequency of a few megahertz, such that you apply the same potential to the opposite rods. So for the moment when you apply negative potential for this is cross-section. Negative potential for these rods, you apply positive potential for these rods. Then, of course, you can also play with the phase shift between the two potentials. Then, in the next half period of the oscillations of this radio frequency source, there will be, instead of minus, will be plus here, then plus here, but then minus and minus there. And one can describe this potential as a saddle, and in the middle of the saddle, in this point, one can place a charged particle. And the charged particle will have the energy, which will depend on the coordinates in the two-dimensional plane perpendicular to the rods. It will look like this. So this two-dimensional plane, this is one axis, this is the other axis. Obviously, positively charged potential is here and there, and negatively charged is here and there. And then the particle is placed in a way that it's sitting on the position of the non-stable equilibrium. But the motion of the particle from that middle point has certain characteristic time. Depending on the steepness of the potential, it will start moving down, but will not really fall down immediately. It needs time to accelerate. But if you rotate the saddle while the particle is trying to fall down, then you can stabilize the particle in the middle. And then basically this is the idea of this power trap, that by applying the AC potentials along these rods, one can stabilize ion in a particular position in the cross-sectional plane perpendicular to the rods. And then one can apply also two potentials from the sides of the rods, and then close the particle in a potential well, in three-dimensional potential well. Of course, this trap is mass selective, is tunable by frequency and amplitude of the voltage, and there are also some DC offset fields one can apply, so there is a whole field how to build those traps. But it works amazingly nicely, and that's an example of one of the pictures maybe like 30 years ago, maybe even more, where you see here luminescence of 4 calcium atoms, ions, excuse me, separated by a distance of about 30 microns. And they are trapped, there are here 4 rods, and then 2 closing potentials from the left and right. So this technique actually allows making ion chains trapped in the in free space, and these chains can be very long. They can be of the length of the order of maybe up to 100. Now, typical spacing is on the order of a few microns, and this can be, of course, controlled by these closing voltages from the left and right. Now, the ions, of course, they are repelling each other. So they are like repelling particles which are sort of pushed in the middle between 2 electrodes from the sides. And they can be accessed by laser beams from different sides to read out their states, to excite their transitions. And readout is very convenient because one can record the fluorescence just by measuring emitted photons with a CCD camera. So this is really very interesting scalable approach. One can make here are chains of ions of let's say a few tens or even up to 100. But how to couple the qubits? This was an interesting question, which was not trivial in the beginning. And then what was clear that ions can be excited in their mechanical motion due to their repulsive interaction between each other and repulsive interaction with the cup electrodes. Now, if you make one ion to move, then you can excite the motion of the whole chain. But the whole chain has, for example, in this picture, this example, it has 5 degrees of freedom. So it has 5 pendula, 5 balls. And if this pendula interact, one can think of different symmetry of the oscillations. Like, for example, there is this lowest energy mode, which is well, all pendula move either to the left or to the right. There is this mode where middle pendula doesn't move, but then others move in different directions. There is also this mode where the motion of the side pendula is opposite direction and so forth. So if one has 5 degrees of freedom, one diagonalizes the equation of motion, one gets 5 eigenmodes. basically the common mode is the lowest energy state because or the convenient mode because all the ions are taking part, and then there is no much difference between them since they all move together. So this is a vibrational motion of particles, and this can be also excited in the chain of ions. And then soon after the beginning of this work, I think pioneers in this field was the group of Rainer Blatt in Innsbruck in Austria. They were able to observe really the vibrational mode of strings of ions, and this is an example. The time goes horizontally, and this is the real coordinate, and then you see that there are this breathing mode of the chain of ions where the chain extends in the lateral direction, but there is also this common mode, as they call it, Schwerpunktsbewegung, which means the center of mass motion. And this is the breathing Bewegung, breathing motion, Atmungsbewegung, the breathing mode. So these modes are possible. But then let's think how these modes are represented in the energy spectrum. And they are represented in the following. So if you move the ions in a particular mode, then the energy of the motion is added to the particular energy state of an ion. Suppose that you have now different ions and one of them is moving, the other one is not moving. Then you will have, of course, the slightly different energy states for those two ions. And when you have emotional state of an ion, then by adding more and more energy in particular mode, by adding phonons one by one into the mode, one can change the energy diagram of an ion from the left to the right, and then more to the right, and so forth. So here you have n phonons in the ion chain. Here you have n plus 1, and on the left you have n minus 1. And the states are slightly different in frequency because they are different by the frequency of this mechanical oscillation. So basically the energy between the difference between the corresponding, for example, lowest energy states of an ion are different simply by h bar omega divided by h bar omega, where omega is the frequency of particular mode. And you could put in this oscillatory mode, of course, any number of phonons you want. So you can change n from minus 1, from 0 to some large number. In fact, these modes are always excited because ions are never quiet. So you need to remove the energy from the ion chain to keep the ions not oscillating. And this can be done by the technique which is called sideband cooling. Basically, you use lasers to take the energy away from the ion chain, and by doing that, you can cool the chain of ions into the ground state. That's really by itself very challenging thing, but it can be easily done by using lasers. So consider that when you apply the transition, the frequency with a laser to excite your ion from ground state to the excited state. You go like in this middle. My mouse is frozen sometime. I don't know why. When you go from the lowest energy state to the highest energy state along this black arrow, you excite an ion from the ground state to the excited state. However, if you have a vibrational mode, then you need already to go to the next excited state, to the state with one more photon, one more phonon in the chain. You need to apply this blue detuned laser, which means a bit higher energy. So by irradiating an ion with the blue sideband laser which is detuned in the blue side, you basically add extra phonon into the common mode. And by applying a laser which is red detuned on the right sideband, in opposite, you remove the phonon from the chain. So basically, you start from the middle here, and then you go with the red arrow to the left, and then by relaxing down to the ground state, by emitting a photon at the main transition, you will have an ion in a chain with one excitation of mechanical motion removed. And that's basically the technique which is used to cool down the chain of ions to the ground state. And then the same technique, the same approach is interestingly used by to entangle qubits by using this mechanical mode. So mechanical mode is often called a bus. It's being used to transfer the information from one ion to another. Suppose that we have now two ions, and we have two ions in the ground state. These ions can be arbitrary two ions of the chain. So it could be neighboring ions, could be also not necessarily neighboring ions, but they are both in the ground state. And then we prepare the motional state n with n phonons in the common mode. Now, once we are in the ground state, we first apply a pi/2 transition to the blue sideband of the first qubit, of the first ion. That means that since we have the qubit there sitting in the superposition with mechanical motion, we'll excite the transition from the state 0, 0, 0 to the state superposition of the state 0, 0, 0 and 1, 0, 1, which means like half excitation will be located in the ion, half excitation will be located in the motional mode. And then we apply pi/2 transition to the red sideband of the second ion, of the second qubit. And by doing this, we basically remove the excitation from this additional excitation from the mechanical degree of freedom, from the bus, from the mechanical motion. But we sort of complete the rotation of the qubit, now making the second qubit half rotating. In this case, we basically prepare the Bell state of the two qubits, 0, 0 plus 1, 1, making both qubits entangled. And moreover, since these qubits we choose by focusing the blue sideband laser on first qubit and focusing red sideband laser on the second qubit, we can entangle any desired PR qubit by using this technique. It's not limited to nearest neighbors. And that's a really beautiful approach that one can use. One can use in this chain. Okay, I don't have this picture here. One can use in the chain basically gates of any qubit with any other. So it's coupling all to all, which is very, very convenient. Now let's see what is the time doing. So how much time I still have? If I'm not mistaken, still like 15 minutes, right?
20 минут закончилось.
20 minutes закончилось. Okay. So the technique to operate those chains is, of course, quite advanced. It doesn't include only this sideband cooling of the chain, but also the standard Doppler cooling technique, which is basically stopping the motion of an object by a laser field. You probably know this from optics. So when we apply a laser and the ion is not moving, then it sees the frequency omega. But when the laser is moving, sorry, the ion is moving towards the laser, then it's the frequency which it sees is shifted upwards. If it's moving away from the laser, it's shifted upwards. It's conventional Doppler shift of the frequency. And then for Doppler cooling, people basically use, they find the Doppler limited emission profile, and then they use a laser line which is detuned, and then red detuned, which means the lower frequency laser. And the excites transition from the in the atom, but basically the photon which will be emitted over all with larger energy. It's in a way similar to what I discussed, but not limited to discrete levels, rather limited to, not limited to that, but rather than simply by gaining the energy of a moving particle by mechanical motion. So basically, by applying the laser at a red detuned frequency, one slows down the laser, and this can reduce the effective temperature down to a few microkelvin. Which means the motion of the velocity of an ion will be corresponding to the temperature characteristic temperature of only a microkelvin, and so forth. So there are also different limitations for that. Now, one use, of course, Doppler cooling in combination with some additional techniques, in particular also using the sideband cooling. And of course, Doppler cooling can be applied to individual ions, and this has to be done also repeatedly, because the ion will get exchanged with the environment and it will slowly warm up. So to be able to cool the system in the ground state, you need to repeat the cooling cycle correspondingly. And typically at the temperature which is achieved by Doppler cooling, there are still about 10 phonons left in the ion chain. So it's not really the ground state. You need to cool down below a microkelvin. And vibrational ground state correspond to 0 phone. So really making this quantum computer work is actually very demanding and requires a lot of patience and tricks. And you may know that the team of Nikolai Kalachevsky succeeded at FIAN cooling down 2 ions to ground state and demonstrated 4-qubit quantum manipulation in Russia. Only, I think it was done last year. But in the West, this has been done already over more extensive time, as I mentioned, by a group of Rainer Blatt and Chris Monroe. Now, sideband cooling technique is used actually routinely, and it's used after the Doppler cooling. And basically, it's done in the following way: that you simply apply a red deacon laser to excite the red sunband transition. And once you do it for all the ions, then all the energy of the system, all the energy of the mechanical motion, one by one, emitting the photons one by one goes away, and the system is cooled to the ground state. And then one can also use the sideband cooling in combination with the manipulation. Of course, manipulation use the same technique of exchange of the energy, exchange of the excitation with mechanical motion. Here, of course, one requires pretty efficient relaxation, and that means one can actually use the sideband cooling using a different transition than the transition which is required for the manipulation. And typically, the remaining 10 photons can be removed by the sideband cooling within time, which is limited by the relaxation of your chosen transition, but practical numbers are as short as 1 millisecond. So once you have done Doppler cooling, by doing the sideband cooling, you cool down the whole chain within less than a microsecond. And the technique is actually having limitations. So the final temperature of the Doppler cooling, so-called, is limited by the recoil. In German, it's called Rückstoß. And this is the remaining momentum after photon emission. So during the photon emission, of course, there is a conservation of momentum, and there will be a minimum energy which is left with the ion after emission of the very last photon, which has a limit of roughly 1.5 microkelvin. So this is a limitation of the Doppler cooling technique. Okay, so I think I gave you the idea of how to initiate, how to prepare the array of ions, how to read them out, of course, without going into details of particular transitions and particular sorts of ions, and also how to cool the chain to the ground state. Let us talk more with wider perspective. Is this approach is feasible for scaling up? So, as I mentioned, by using these long chains, one can realize mechanical chains with, let's say, a few tens or even hundreds of ions. However, the number of vibrational modes which exist in the chain increases greatly, and with increasing number of degrees of freedom in the chain, you have more and more different modes, and they start to cross and overlap, and the system, the frequency space becomes very quickly crowded. So, and also you need to cool down not only one mode, you need to cool down all those modes. So basically, to avoid mechanical motion, you need to cool down at many different frequencies. So really, the task becomes very, very complex as the number of modes increases. The approach which people followed until now, this is the group of Monroe and the group of Blatt, was really to demonstrate algorithms with high fidelity, and they managed to demonstrate algorithms with very high fidelity and fidelity of the readout of 99.some%. However, really doing the scalable approach where one would be able to have as many traps as possible and then entangle them, for example, by using the photons, has been less explored. But there is another approach which has been recently overtaken by industrial partner, Honeywell. I will tell you a little more about that. Here you see a kind of a photographer view of the lab of Rainer Blatt in Innsbruck. This is Chris Monroe. Actually, both visited Russian Quantum Center many times and gave talks at the conferences in quantum technologies over the last 10 years. This player, which I mentioned, is the company Honeywell. Honeywell has been founded less than 10 years ago. And in the year 2021, last year, they reported a scalable approach to quantum computing. So they went along development of the so-called ion chips. So instead of using the three-dimensional rod structure, which of course is macroscopic and well established and so forth, they worked on the approach of microfabricate particular configuration with alternating electric fields using on-chip electrodes. And here you see the construction here. It's placed somewhere here in high vacuum. So this construction has a semiconductor chip which has different metallic layers and gaps between them. And you see here that ions, they move from different locations, which are colored here by blue and yellow and orange and so forth. Now, the green lines are RF electrodes, which are shown to be 2 here. I think probably more than 2. There is also the ground oscillating field. I'm not sure, but they don't disclose this. And it's also not my field. But then these different colored spots are DC electrodes, which are used to manipulate ions in a very fine fashion. And they have chosen the approach where they use as a qubit combination of 2 ions. One ion, in particular a barium ion, 138, is used for cooling and is coupled to a nearby ytterbium ion, ytterbium 171. It has a transition at 12.6 gigahertz, rather convenient for manipulation. And then every erbium ion is always carried nearby barium ion. And then DC electrodes are always used to move those pair of ions around back and forth. They even learned how to swap the position of ytterbium and barium ions. So one is basically a refrigerator which cools down ytterbium nearly continuously, or kind of when the manipulation is interrupted. And then ytterbium contains the quantum information and is being used for storing quantum information and for reading. And they used, for 2-qubit gates, they used barium, ytterbium, ytterbium, barium states, and also for manipulation, ytterbium, barium, barium, ytterbium states. I believe this is kind of coupled qubit, and this is probably the interaction switched off. All is controlled by high efficiency electronics with FPGA and use machine learning mechanisms or techniques, algorithms to learn manipulation of ions. Really very, very advanced technology. And by doing this manipulation, they were able to implement all the relevant steps. So they were able to store information, to apply gates, then apply gain gates, and then to read out the information and load the ions in a different register. So there is a very long paper, amazing paper published in Nature last year on that subject. So this illustration shows you single qubit gates and 2 qubit gates implemented between different pairs of ions. I still have slides today to tell you a little bit about atoms, but I would rather not mess around with that. It's only 3 minutes left. Let me ask you if there are questions. So I'll stop today at this point, and we'll start with atoms next lecture. Let me ask you if there are questions. Was it too simple? Or you got tired after 2 lectures? Tell something, please.
Ну, много было понятно, и часть мы знали про охлаждение атомов, например.
Ну,
Ну и про ионы.
Ну, я старался, чтобы было совсем просто, конечно, поскольку это не моя область, это скорее просто как бы такой рассказ беллетристический о том, как критерии Ди Винченцо выполняются на разных системах, чтобы вы могли сравнить и отчасти понять, в чем, собственно, преимущество масштабируемого подхода на сверхпроводниках.
Да не, хорошо вышло. Вот если касательно Мессиса просто, у нас еще куча других тоже курсов, и они почему-то очень сильно похожи, поэтому мы, наверное, вот в n-ный раз все слышим. Ну вот, я думаю, они ближе вот к середине уже начнется что-то такое уже конкретно каждому курсу свое. А пока все, все хорошо, понятно.
Ну хорошо, главное, чтобы
Спасибо
вы
вам.
не разбежались, не главное, но я надеюсь, что вы не все разбежитесь. Вот. То есть, конечно, сложность будет возрастать, и пока мы как бы говорили только о базовых вещах, которые вы уже слышали из других курсов, но дальше сейчас вот постепенно еще будет у нас такого обзорного вида следующая лекция. Ну и дальше уже вживую, я надеюсь, в Москве мы займемся сверхпроводниками. Напоминаю, что это будет 22 и 29 ноября. Я надеюсь быть живой в Москве и всех вас повидать. Скалтихи. Хорошо, тогда на этом давайте сегодня закончим. Спасибо всем за внимание. Вот. В следующей неделе. В следующий вторник.
Спасибо.
Вам спасибо. Спасибо большое.
Спасибо.
Можно вопрос задать?